Namaste. Welcome to the lecture series on the subject Basic Thermodynamics, Module 3, Part 2, Entropy, Lecture number 12. Myself, Dr. Nsatheeshkumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Bantwal. So the contents for this topic are property diagrams using entropy as coordinate. Actually, it is a very small lecture. Okay. So now we will study the property diagrams with entropy as coordinate. Now as you can see here a TS diagram. So entropy as coordinate means usually entropy will be on x-axis, and the general diagram using entropy as a coordinate will be the TS diagram, where the temperature will be marked along the y-axis. Now this is the phase change diagram for a pure substance. Okay, you can see the line here from here to here. So this is called as saturated liquid line. That means it is a point where the phase change from liquid to vapor begins, right? So to the left of this, so this region, so it will be completely liquid, and from the, this is called as the critical point. So more about this you will come to study in the chapter pure substance, so I am not going to explain this much. And this part, it is known as the saturated vapor line. So beyond or right of this, it is the vapor region, you can see here. Okay, so this is a critical point where the latent heat of evaporation or is 0, or entropy is also 0 when the substance changes from the liquid to vapor phase. Now this is the dome, the area inside the dome, so that represents the liquid plus vapor region, and within this dome, see, these are the constant pressure as well as constant temperature lines. Okay, so here it is constant temperature line, so your pressure also remains constant. Okay, and here before this to the left of the saturated liquid line, you can see here, so this is the constant pressure line, but here from this point onwards it passes through like this, and then it goes like this, the constant pressure line. Okay, so same line represents constant pressure as well as constant temperature, indicating that during the phase change of a substance the temperature and pressure remains constant. Now all of you know that the area on the TS diagram has the dimensions of heat. That means area on a TS diagram represents heat. As all of you know, the area under PV diagram represents work. Okay. Now in the mixed phase region, the constant pressure and temperature lines are horizontal. Okay, that is what I told just now. Now coming to this diagram on the left side. Okay, so here that is the processes on TS diagram. Here you can see two vertical lines shown here. See here, for this line, now it is a process wherein the temperature increases, so you can call it as heat addition process. And if you come down here, you can see the entropy change is 0 for that process. If you take this is state 1, this is state 2. Okay, so entropy change is 0. That means such a process is called as isentropic process or reversible adiabatic process. So this is a heat addition process. Now this is a heat rejection because temperature decreases. So for that also, so there is no entropy change. So if there is no entropy change, so it is indicates that there is no heat transfer. If there is no heat transfer, so then the process is adiabatic. Okay, so no heat transfer, no entropy change, so then it is called as the reversible adiabatic. Now if there is a change in entropy like this is as shown in the dotted line, and or as shown here, you can see this line would have been vertical actually, but because of the irreversibility, so this is not vertical. So from the state 1, so this is state 1 to state 2, so instead of coming vertically downwards, so it has come like this. Okay, So indicating that, so there is some entropy change. You see, this is the entropy change. So if the factors affecting irreversibility causes entropy change during the process, though there is no heat transfer between the system and the surroundings, then it is called as irreversible adiabatic process. That means there are some factors which causes irreversibility, adds to heat and results in increase in entropy. So here also instead of the process going vertical like this, so now it is going along this dotted path, right? Once again, due to the factors affecting irreversibility leading to change in entropy. You see, change in entropy you can find out. So that is this gap here. Okay. So that is called as the irreversible adiabatic process. So in a reversible process, the area under the curve is equal to the heat transfer corresponding to the process. Okay. So in a reversible process, if the process is reversible, so then only you can take the area under the curve as equal to the heat transfer. Okay. The vertical lines represents the isentropic process. So that is what I explained in the previous slide. In a reversible cycle, the area enclosed by the curve representing the process is equal to the net heat transfer. You see, area below the curve is the heat transfer for that process, whereas area enclosed by the curve for a cycle, the cycle means starting point and the final end point or end state has to be same. So number of processes in sequence bringing the system back to its initial state is called as a cycle. So here it will be complete area, enclosed area, right? So the area of that enclosed part, okay, so that is equal to the net heat transfer to the fluid, okay. And so from the first law is also equal to the net work, because for a cycle, cyclic integral of dq is equal to cyclic integral of dw. So here very important part is, so for a closed cycle, for a reversible cycle, so whatever the area enclosed by the TS diagram which represents heat transfer is also equal to work transfer. So that is very, very important thing you have to note down. So this is for a reversible cycle. Okay, now let me explain you Brayton cycle as an example on the TS diagram. So this is a cycle for the gas turbine which you will come to study in the next semester in the subject applied thermodynamics in the chapter gas turbines. Now let me restrict my explanation only to the TS diagram. Okay, so here let me start explaining from state 1. So this is the entry point to the compressor. So 1 to 2s you can see here. So this is a compression process in the compressor, and it is 2s indicating that it is isentropic compression. 1 to 2s is isentropic compression. So this is ideal process. So let me explain the ideal process first. Then 2s to 3 is a constant pressure heat addition, and 3 to 4s is isentropic expansion in the turbine. Once again, this is the ideal process. The process is theoretically said to be taking place isentropically or reversible adiabatically. Okay, and 4s to 1 is the constant pressure heat rejection. So if the all processes are ideal, so this is the cycle. But as you know, in the compressor and the turbine, the compression and expansion doesn't follow the ideal process. This is mainly because of the irreversibilities. So there is some deviation. So this dotted curve you can see 1 to 2. So that is why it is marked as 2, indicating that this is the actual process. So now because of this irreversibility, so entropy change is there. You can see, 1 to 2s vertical line, there is no entropy change. If I come down, 0, change is 0. But 1 to 2 you can see, so S2 minus S1, this gap is there. So this is the entropy change. So this results in additional work input for the compressor. Similarly, the expansion in the turbine doesn't follow the ideal process or isentropic process. Instead, it follows the dotted line like this, so indicating that there is some deviation from the ideal process. In the actual process, once again there is some entropy change. Now you can see here, so the final state after expansion is here instead of here. That means the work output becomes less for the turbine because of the irreversibilities. So irreversibility is the biggest loss to us. Suppose if it is a work absorbing device, so you need to supply more work to the device, and if it is a work producing device, so it produces less work output because of this irreversibility. So here my intention is to explain the actual process and the ideal process of compression in a TS diagram. Specifically I am concentrating on the isentropic process because I am explaining the TS diagram. Now this TS diagram can also be used to find the Carnot efficiency of a Carnot engine or efficiency of a Carnot engine. Now you know that this is a diagram. You can see here A to B is the isentropic compression, and B to C is the constant temperature heat addition process. So here actually the QH heat addition takes place in the cycle to the working substance from the high temperature reservoir. Then C to D is the isentropic expansion, and this is the heat rejection again at constant temperature. So amount of heat rejected is QL. Okay. Now as all of you know, so the area under the curve represents the heat transfer. So A to B vertical line, so there is no area, you can see it is vertical line 0. So isentropic compression. Okay. So isentropic means reversible adiabatic. Adiabatic itself is a word used for a process where there is no heat transfer. So straight away I can say that there is no heat transfer during process A to B. Now B to C, so just now I mentioned that there is heat transfer QH from the high temperature source to the working substance. Now the process is B to C, so the area below this line B to C. So what is this below line? That means from R, okay, to B. So I'll show it by a different line, blue color. So I'll just draw inside the actual line to show the. So this rectangle, you see, RB CE back to R. So this is the area below the line BC. Can you see here? This is the line BC. So below that, this is the rectangle. So this area is nothing but, so from here to the vertical height, is length into breadth. So this you can take it as length from here to here, and this difference you can take it as the breadth because it is a rectangle. Area is length, this is length, and this is breadth. So length is nothing but from this is 0. So from here to here the length is nothing but the temperature TH. You can mark, you see it's marked here, temperature TH. And the gap from here to here is nothing but entropy at SE minus entropy at SF, because it is 0, right? So from here to here is entropy SF, here to here is entropy SE. So this gap, okay, between these two is nothing but SE minus SF. So this QH now becomes TH into, I'll write here QH, okay, is equal to TH into SE, this is E, okay, minus SF. So I am not able to write properly, okay, using cursor, so you can understand. This is QH. Now C to D, once again isentropic expansion process, being isentropic process, no heat transfer. D to A, you can see here, D to A is a heat rejection process. So I told you that QL is the amount of heat rejected, which is represented by the curve D to A, or area under the, represented by the area under the curve D to A, area under the curve D to A. That means this area, you see, this area. So that is nothing but this vertical height from here to here, and the width is same. You see, this line is same again, from here to here it is same. Let me use a different color. Okay, this color that is not suit, doesn't suit. Okay, let me use this color. Okay, so this length, you see, from here to here, here to here, once again it is SC minus SF. So this length is SC minus SF, but here this length is from here to here, it is TL. So QL is nothing but TL into SC minus SF. So better all of you note down, okay, all these things for better understanding. Okay. Now you have to find out the efficiency of the Carnot cycle. So I will explain that in the next slide. Okay. Now let me derive the efficiency. So all of you know, okay, before that, you see, now this line represents heat addition process, okay, QH. So entire area below this, so let me hatch that. So that is why I changed the slide, because there were so many lines on the previous slide. So this is the heat addition, and area below this curve, let me change the color. This curve is the heat rejection. So this part area is the heat rejection. Now net work done, W, as all of you know, is nothing but QH minus QL. Okay, QH minus QL. So I am going a little bit depth to explain you everything about Carnot cycle. So area below this is QH, area below this is QL. So QH minus QL is this area. You see, this yellow color area. So this is QH minus QL. So actually this is the nothing but the net heat transfer during the cycle A, B, C, D, because it is representing cycle A, B, C, D, A. So area A, B, C, D, A is representing the net heat transfer, that is nothing but QH minus QL, which is also equal to W as per the first law of thermodynamics. So that is what it is indicated here. This is QH minus QL. And you know that efficiency of the Carnot cycle is nothing but QH minus QL, which is nothing but W net actually, W net, which is nothing but QH minus QL divided by QH, because out of the total heat input, what fraction of the heat is converted into work. So QH minus QL is represented by this yellow color area here, right? This yellow area, which is nothing but area ABCDA, and QH is nothing but the area below the curve BC. This is nothing but, this is F actually, okay, F B C E A, okay, F B C E A, F B C E F, sorry, F B C E F, okay, it is written here F B C E F. So this is the area representing the heat transfer. Now in the previous slide itself I told you that this QH, you see this QH here, let me use different color, is nothing but TH into SC minus SF. Okay, maybe in the previous slide I used this as R, okay, it's not R, it is F, okay, and TL, QL is nothing but TL into SC minus SF, okay, TL into SC minus SF. This is I am taking from the previous slide, and QH is also equal to TH, QH you have to substitute as TH into SC minus SF. Now SC minus SF gets cancelled from all the terms, being it's common, so it becomes TH minus TL by TH, or efficiency becomes 1 minus TL by TH. So this is already you proved, but you proved it by some other method, by taking the work done, calculating work done during the isothermal expansion and the compression process, but you got the same answer. So here this is derived using the TS diagram. Okay. Now coming to the last slide, so enthalpy, entropy, or the HS diagram or the molar diagram. In fact, so I'll be restricting myself to a bit of explanation on this, as this will be dealt in detail in the chapter pure substance, wherein to study the properties of water as a pure substance or vapor as a pure substance, you have to look into this diagram. So here the y-axis is nothing but the enthalpy, whereas the x-axis is the entropy. Okay, and here like that TS diagram for a pure substance I have shown. So this is the saturated liquid line here, saturated water or liquid line, and beyond this is a critical point. So after this part, so it is a saturated vapor line, and this region is below this line, saturated line. So this is a saturated liquid, this is a saturated vapor from here, this side is saturated liquid. So below this phase is the liquid plus vapor region, you can see L plus V, and this side you have the liquid, and after the critical point, this side you have the vapor, and this part it is superheated vapor, because anything above the saturated vapor, so that is the superheated vapor, and all these lines are the constant pressure lines. Okay, and here all these lines are the constant temperature lines. So I am not going to deal much about this chart now. So when it comes to the pure substance, so I will explain you more about this. Okay, thank you. So with this I conclude the lecture number 12, and I finished the theory portion as per your syllabus, and will start numericals in the next 3 lectures. Thank you.